Hello, everybody. Be welcome to my session. My name is Sarah, and today I'm going to talk about signaling task groups on a real-time fashion. So first of all, I would like to talk about my relation with Nuttx. I'm currently working at Expressive System as a junior embedded software engineer, and I work on the port of Nuttx to Expressive chips, like for example, ESP32, ESP32C3, and more recently ESP32S2. So what is this presentation about? This presentation has a goal, and the goal of this presentation is to show you how to signal to multi-thread task groups, and from this signal advertise other children threads that may be waiting for this signal to act, to do some to perform some action. Okay, and to achieve this purpose, we need to cover some prerequisites, some topics, like for example, the difference between task versus threads, what is a task group, and why not a process, and also how to achieve a signaling on a deterministic with a deterministic wake up time. And why is this important, and why did I decide to talk about this? First of all, this idea came with actually my interest on signaling, on threads, on task, and all this stuff. It started when I started to develop the timer driver. And I realized that when we are using the timer driver, we can't register a callback to be called by the ISR of the timer driver. We need to configure a notification. So the time when the timer expires, it will send a signal through this notification. And then I started to study about this, and also realized that it's kind of a fuzzy content. There are many documentation spread regarding this aspect, and mainly when we are talking about signaling multi-thread task groups. So it's also a kind of overview that I'm bringing here in this presentation. It also may be required in your application if you are using task groups and you are using signals. So how are we going to explore it? What I'm going to do after presenting these topics for you is to present a simple application that uses signaling to multi-thread task groups. So first of all, what is the difference between task and threads? This is a difference in Nuttx that may be not present on other operating systems. So tasks, when they are created, they create private resources that other tasks may not be may not should not access. And when a thread is created, it will share this task resources. So basically that's the difference. They share the task resource, like for example file descriptors, file streams, and so on. Threads, they cost less memory, and when a task is created, also a task group is created along with this. And the task group emulates a POSIX process. So it's not a POSIX process, but it works like a POSIX process. And the threads become part of this so-called multi-thread task group. Okay. This task group is very useful when, for example, we are not using the kernel mode, when we are using flat mode, or when we are using protected mode, because process in Nuttx are not available on both flat and protected mode. So here is a simple draw that can expose the idea of a task group. We have a task, and then we have the children threads here, which become part of this task group and share the resources of the task. Okay? So process. Why not process? A process requires a memory management unit to protect its address space. And Nuttx was designed to support not only microcontrollers that support MEMU. It also was designed to support microcontrollers that does not contain a memory management unit. And so when we have a less robust microcontroller that does not contain MEMU, it would not be possible for this microcontroller to have a process. So in this case, we have the task group that emulates a POSIX process. Okay, but if you have, for example, a MCU that contain memory management unit, you can use the kernel mode and you have a complete process, POSIX process compliant. So let's move on and talk about signaling. Signals are used to notify events between tasks or within a task context, okay, between threads, for example. And there are basically two mechanisms to catch these signals once they are sent. We can use signal handlers, which is a not very recommended solution because it has a long latency, and we can use waiting functions like the one that I'm going to present when we see the code. And these functions is very important if you want to have a deterministic time between when the task sends a signal and the another task or thread gets the signal. But for this, you need to set the task that is waiting for the signal a high priority. So this is suitable for the real-time applications, and this is the part of real-time from this presentation. So when we are signaling to multi-thread task groups, we have to keep some things in mind. The first thing is that the behavior of a multi-thread task group depends on configurations. So you may create a task, you may create threads inside this task, but if you don't enable the required configurations, you are not going to have the expected behavior documented in Nuttx, what is expected. Second thing is that the behavior also depends on the signal set, the configuration of the signal set from your main thread and from the children threads. And also one thing that I would like to talk is what if the main thread dies? Okay, so let's dig a little bit into signaling to understand what happens when we have a signal. Well, signals are initiated through an XSIG-Q, an XSIG-Q, an XSIG notification, and they all will call an XSIG dispatch. And this function will behave different if we have this definition defined, this macro defined, have group members, and it will behave different if we have not this macro defined. So if we don't have this macro defined, it will not follow the roles for signaling multi-thread task group. You're going to read one thing in the documentation and it will behave in another way. Signal will be dispatched to the specific PID used. So in the next slides, we're going to see that doesn't matter the pthread ID when we are signaling to a task group, we're going to use the ID, the PID of the main thread, okay? So, but if we not enable, if we not have this macro defined, we're not going to have this behavior. And so how can we have this behavior, the correct behavior? We can have the correct behavior by enable these two configurations, scad have parent and scad child status, okay? These two configurations together, they allow a relationship of parent and child between the task that created the threads, and it also allows to retain the exit status of the threads, of the children threads. So regarding the second topic, behavior depends on signal set. When you enable these two configurations, what will happen is that once you send a signal for the task group, the thread that will receive, that will catch that signal, is not well defined. It will be any thread that's not blocking that signal. Okay, so here in this draw, what we have is, for example, we sending the signal number 17 to the PID 3, which is the PID of the main thread who created these threads. What will happen is that one of the threads that is not blocking, I mean, for example, here, let's say that thread 3 is blocking signal 17. So this thread will not receive the signal 17. But if thread 1 and thread 2 are not blocking the signal, or both of them are waiting on this signal, we can't define which one is going to receive the signal. So that's why the behavior depends on the signal set. The behavior of signaling for multi-thread task group depends on signal set. We have to configure our signal set in such a way that we can define who is going to receive the signal. You may also observe here that I use the PID of our task, because other tasks are not supposed to know pthreads IDs. But if we are in protected or flat mode, that's possible, but that's not supposed. But other tasks are not supposed to know pthreads. So you should not use the pthreads. You should use the task ID. So, what is a strategy to ensure that a specific thread will receive that signal? One strategy is that we can take advantage of one thing. Pthreads inherits signal mask of the task that created them. So you can create a task that blocks all signals, and then when in the pthread, in the specific thread that you want to receive the signal, you unblock it. And how you can do this? How can we achieve that? By using, for example, sigproc max, pthread sigmax, which we can define which signals we want to block or which signals we want to unblock. Okay, and the last thing to have in mind when signaling for multi-thread task group is, what if the main thread of the task group exits? What will it happen? What will happen is that all the children also dies. So you need to keep the main thread alive to keep the task group alive. So now that we have covered some of the basic concepts regarding task groups and multi-thread task groups and signaling multi-thread task groups, we can finally work on that, and I will show you how to do it. So what I'm going to present in the following minutes is a simple application. This application is basically composed of one task group, this task group here. This task group has two children threads in the main task, the main thread. This main task, as I said to you before here, it can't die, because if it dies, the threads also die. So we're going to use the pthread join function. So it will be suspended and wait until the children threads finish their work. And here in thread 2 and thread 3, we have the signal blocked. Okay, this symbol means that we have the signal block. And on thread 1, I'm going to unblock one signal, which is the specific signal that I'm going to configure for my timer callback to send through NX SIG notification. Okay, the thread 1 is going to be waiting for the signal using this API SIGWait info, which, as I already said before, is better than signal handlers because it has a wake up time deterministic, mainly when this thread is with high priority. And what we're going to do is, every time that a signal is catched here by thread 1, we're going to post on both semaphores, semaphore of thread 2 and semaphore of thread 3. Semaphore of thread 2 and semaphore of thread 3 are the same, and they are only waiting for the right moment to perform some action. This right moment is at timer's expiration. Talks ship, show me the code, as our friend Linus Torvalds says. So let's going to move to the code. Here we have the main thread of the task group and the pthread that gets the signal, and here we have the other pthreads that are waiting for the signal to take some action. I'm going to move to my code editor to show you in details and also to run this application. So here we have the okay, let me show you the code. Okay, here we have the main task, and the main task initializes doing what? It initializes the semaphore, the semaphore that will be used by the thread that receives the signal to unblock the other threads. And here we are going to configure the signal set for this task group. First of all, we're going to initialize the signal set with all signals, and then we are going to call sigprogmask to block all the signals in the set. Since we have used sigfillset, we are blocking all the signals. Then in this snippet, what we basically do is to create first the pthread that I call it pthread man or pthread or thread manager, which is the one who is going to receive the signal. And then we loop, creating multiple threads that I called thread workers. They are simple threads that do the same thing. They will only print like a hello and a hello with their index, and their index I'm passing as a parameter here, is a pthread parameter. So then I call this function, which is the timer setup, where I configure the timer callback to notify the task group through one specific signal, and passing the PID of the main thread of this task group. And then we go to a loop where we're going to wait for all threads finish. And when all threads finish, the workers in this case, not all threads, but the workers thread finish, we stop the timer and we exit from this and we finish our task group. So first, let's go into take a look on the manager pthread, the thread that will receive the signal. Here we also initialize a set, but in this case an empty set, not containing no number, no signal number, and we add only the signal number that we configured in the timer, for the timer to notify. And we use the sigmask now to unblock this signal on this set, because since this pthread inherits the signal, the signal set, the signal behavior from the main thread, what it's going to happen is that if we do not do this, this thread will not unblock the signal. So here we go to a loop, and in this beginning, we're going to, this thread is going to suspend until the signal is unblocked, not sorry, until the signal is pending, or until the signal is received. So once the signal is received, it's going to print received signal, and it will loop on this for and post on the thread semaphore to unblock all the threads that are waiting on a semaphore. So here we have finally the thread worker, which is basically a simple thread that will loop in this while 2 times. It will wait on the semaphore to be unblocked by this pthread, and once it is unblocked, what it's going to do is print a hi from and its index, its number. It will loop again, so when it's executed 2 times, it will leave, and finally pthread join from the main task is going to return. Okay, so let's take a look on this working, on the execution of this. I have I'm using here my ESP32 chip. I don't know if I can, my cable is very short to show you. So I have already downloaded this application, and what I'm going to do here is to reset my board and then execute my application, which name is test group. Okay, so now I configured the timer like 2 seconds, and we can see here that we received signal 2 times, and we had the 2 worker threads saying hello and showing their index, and we can type here PS, and we can see that we have no more threads, or the task who created these threads. So it concluded okay. Now we can move on and back to our presentation. Okay, so here is the end of the presentation. I left here some of the references that I used to this presentation. I hope you can enjoy it, and thank you very much for attending to my session. Bye bye.